conductive position sensors, wireless and wired communications, authentication, SMPS, DC-DC conversion, and power over Ethernet. Bob has 12 US patents and multiple publications and blogs. After the presentation, we'll have a live Q&A with Bob, and you guys can, in the audience, can submit questions anytime during the session using the chat box tab that you see on your right-hand side of your screen. So thank you so much for joining, and with that, I'll hand it off to Bob for the presentation.
Hello, everybody. For an agenda today, we will begin with our switch mode power supply matrix from 5 watts to greater than 3 kilowatt, and that includes controllers, gate drivers, and switches. Then we'll move on to switch mode power supply block diagrams, a total of 11 of them, ranging from 5 watts to 3 kilowatt or greater, correlating to the above matrix. And again, that includes controllers, gate drivers, and switches, and we'll also have a 1 slider on our wide bandgap silicon carbide. And then we'll wrap it up with reference designs and a demo block diagrams, including USB-C power delivery for 65 watts and 100 watts, a 3 kilowatt power supply, followed by a 7.2 kilowatt onboard charger. So anything that plugs into a wall, from a coffee pot to a blade server, needs a switch mode power supply to convert AC power to DC power. But the problem is that many of these different power supplies, whether they're 5 watts to 65 watts, or moving up to like lighting or power tools, 70 to 200 watts, and you keep moving up the power tree, you know, the power levels, TVs, power e-bikes, charging e-bikes, where you're to 200 to 350 watt, or you go to 350 to a kilowatt for cobots, medical equipment, microwaves, or finally up to a kilowatt to 2.5 to 3 kilowatt, where you're looking at HVAC and white goods or a cloud server. They all require different power supplies based on the amount of power required. And it's tricky because the irony is that they all have the same topology, right? You have AC power on the left side, DC power on the output on the far right side. In between, you have a transformer, and on the left-hand transformer, you have primary side control, and the right-hand side, you have secondary side control. So they all share a common topology, but your choice for the controllers, whether it's power factor correction, active clamp flyback, quasi-resonant flyback, or synchronous rectifier controller on the primary side, or the secondary side, or the gate drivers you choose, or the switches you choose, MOSFETs, IGBT, silicon carbide, or GaN, you know, there's a lot of decisions to be made to fit the right power supply to the right power level. So where do you start? And the answer is easy. You start with onsemi conductors, easy to use switch mode power supply matrix on the next slide. So this easy to use switch mode power supply matrix is a guide, or a first order approximation guide, to help guide you through selection of the controllers, gate drivers, and switches based on the power supply. And so all the columns contain the controllers, gate drivers, and switches, and the rows capture the levels of power, where the bottom row is the lowest power and the top row is the highest power. And we see an NA, that just means it does not apply. You don't need anything. So we'll start here. For the very first 3 rows are 5 watts to 25 watts, 25 watts to 50 watts, and up to 65 watts. And you move over to the right, and wherever you see an NA, you don't need anything. But when we see a product, that's the product you would pick to build your power supply. And further on, I'll have a block diagram of each one of these rows so it's easier to visualize. So then the next set of rows, I have 70 watts to 200 watts, and we have two sets of rows, ultra high density and high density. Ultra high density means you pay a little bit more money, but you can shrink the footprint of your power supply for the same amount of power. The next set of power is 200 watts to 350 watts, where you have ultra high density, in the middle there, low profile. And so that just gives you some more options for the form factor of your power supply. And then above that, we have 350 watts to a kilowatt at ultra high density and high density. And finally, the top 2 rows are 1 kilowatt to to 3 kilowatt or a little bit higher. Now the first two columns capture the power density rating, either ultra high density or high density, or in one case low profile. And then the next column is the rectifier. And you can see there's a number of products that you can use for your full wave rectifier, moving up and down the power levels for each row. And there is also a bridgeless. And so the bridgeless kicks in when you decide to use power factor correction, which is required for going over 75 watts. One of the options for a power factor correction is a totem pole PFC, where you don't need a rectifier. Now a PFC, what it does sometimes with varying loads is the voltage and current goes out of phase. And that's why after 75 watts, you typically want to have a power factor correction. What it does is it basically puts in phase your voltage and current. And so for PFC, you can just have a regular PFC controller, which I've listed here, a number of different PFC controllers. And you'll notice I have NAs at the bottom under 65 watts because you don't really need a PFC until you're above 75 watts. So if you keep going to the right, that's the power switch Q1 that you would use with that PFC. Now, as I mentioned earlier, totem pole PFCs, which are very nice for efficiency and are typically used for higher power, would also have a slow leg and a fast leg switches. So these four columns capture the gate drivers and the switches if you plan to use a totem pole PFC. And so where it says NA, those are not totem pole PFCs. But where I have the gate drivers and the switches, those would be totem pole PFCs. Again, further down, I'll show the block diagrams, which is a better visual for all these different power levels. Next is the active clamp flyback, where we have a couple of instances for the active clamp flyback. And then next is the quasi-resonant flybacks, and that includes the controller and the power switch, followed by the LLC, which are also controllers that are used, they can switch faster. And if they can switch faster, your passives, the inductors, the capacitors, and the transformers can typically be smaller. So you typically use LLC for your higher power, as you can see when you're getting over 200, 350 watts. We have our LLC controllers listed there, as well as the gate drivers and the switches. Now finally, the column for the primary side, the last column, we have the switchers, and you can see those are all NAs until you get down to up to about 50 watts. And you can see we have a couple of switchers there for 5 watts to 25 watts and 25 watts to 50 watts. And those are basically flybacks with integrated power switches. And then next we go to our secondary side controller, where I've captured the controllers for the secondary side and their switches. And then finally, the last two columns is USB-C power delivery, where we have a number of different controllers and V-bus N-channel MOSFETs to enable the V-bus onto the Type-C connector there. So this is a summary of our easy-to-use switch mode power supply matrix. And the next group of slides, I'll walk through all these, each one of these rows, but in a block diagram format, so for easier visibility. Okay, now we're going to turn our attentions to a total of 11 switch mode power supply block diagrams from 5 watt to 3 kilowatt, correlating to the previous matrix slide for high density and ultra high density power ratings. Okay, for our 5 watt to 25 watt power supply with a DC output of 5 volts to 36 volts, at the AC input on the far left, the DF10S or the DF08S diode bridges are recommended for full wave rectification. In the secondary side on the right, the NCP431 shunt regulator is a low tempo programmable voltage reference up at 36 volts with only 2 external resistors. The FOD817 optocoupler provides isolation feedback from the required Vout in the secondary side back to the NCP 10.7x flyback controller on the primary side in order to regulate the V out with varying loads. The NCP 10.7x is a family of what we call switchers, which are flybacks with integrated power switches, in this case rated for 700 volts breakdown voltage, up to 130 kilohertz switching speeds. You can choose either the 1071, 1072, 1075, 1076, 1077, or 1079, depending on the required current limiting correlating to different power switch RDS(on). Please visit onsemi.com for more product information. Now, moving to our 25 watt to 50 watt power supply, the secondary side on the right does not change, but for the primary side on the left, we transition to the GBU4M or the GBU4K diode bridge for higher power. We also pivot to our 800 volt, 130 kilohertz switchers, the NCP 11184 with a 2.25 ohm RDS(on) maximum, or the NCP 11185 with a 1.3 ohm RDS(on) maximum, or the NCP 11187 with a 0.87 ohm RDS(on) maximum. And finally, moving to our 65 watt power supply on the primary side, we replace our switchers with the NCP 1345 quasi-resonant flyback, which operates up to 500 kilohertz and supports valley switching for improved efficiency. The NCP 1345 drives the NVD260N65S3 650 volt, 260 milliohm external power switch. On the secondary side, we use the NCP 4306 secondary side controller to drive the FDMS86180 synchronous rectifier switch, rated for 100 volts, 3.2 milliohms. The NCP 4306 supports 7 amp sync current and 2 amp source current gate drive. And for USB-C power delivery applications, we offer the FUSB 15101 PD port controller, supporting up to 100 watts PPS or programmable power supplies from 3.3 volts all the way to 21 volts per the USB 3.0 PD specification. Next, we can look at the high density block diagram for 70 watts to 200 watts, where on the input of the primary side on the left, we select the GBU6M or GBU6K diode bridge, followed by the NCP 1623 PFC controller driving the NTP125N60S5H 600 volt N-channel 125 milliohm power switch. The NCP 1623 is a compact, robust, and feature-rich valley switching PFC controller with frequency foldback optimized to achieve high efficiency across a broad range of loads, while offering a complete suite of system-level safety protection. The NCP 1623 PFC is followed by the NCP 1343 quasi-resonant flyback, featuring a proprietary valley lockout circuitry, ensuring stable valley switching. The NCP 1343 drives the NVD260N65S3 650 volt, 260 milliohm external power switch. On the secondary side, the NCP 4307 synchronous rectifier controller can be configured for high side or low side configuration. For 70 watts to 200 watts, we recommend the NTM FSC010N08M7 80 volt 10 milliohm N-channel MOSFET. For up to 100 watts, the FUSB 15101 USB-C PD controller is a great choice. And for ultra-high density, on the primary side, the NCP 1568 active clamp flyback can be used in conjunction with the NCP 51561 5 kV galvanic isolated dual gate driver to drive two NTH L045N065 SC1 650 volt 32 milliohm silicon carbide MOSFETs. The NCP 1568 active clamp flyback replaces the RCD clamp snubber diode with one of the two SiC MOSFETs, improving efficiency while protecting the other SiC MOSFET power switch. Moving on to the 200 watt to 300 watt high density power supply, we are looking at either using the GBU8M or GBU8K diode bridge, followed by the NCP1616 PFC controller driving the NVB190965S3F 650 volt 190 milliohm N-channel MOSFET. The NCP1616 is a highly efficient and compact CRM or critical conduction mode PFC controller with high voltage startup capability. The current controlled frequency foldback technique enables superior nominal and light load efficiency. The NCP1616 PFC drives the NCP13994 LLC controller, which drives a half bridge consisting of two NVB150N65S3F 650 volt 150 milliohm N-channel MOSFETs. The NCP13994 is a high-performance LLC controller supporting 700 volt startup, switching frequencies from 20 kHz to 750 kHz, quiet skip mode for reduced audible noise, and 2 amp source and sink gate drive. On the secondary side, we find the NCP4318 synchronous rectifier controller driving two NTM FS6H824N 80 volt 4.5 milliohm N-channel MOSFETs configured in a half-bridge topology. The 4318 is an advanced synchronous rectification controller for LLC resonant converters with minimum external components. It has two gate driver stages for driving the synchronous rectifier MOSFETs, which are rectifying the outputs of the secondary transformer windings. The two gate driver stages have their own drain and source sensing inputs and operate independently of each other, and an advanced turn-off control algorithm allows stable synchronous rectification operation over the entire load range. As for the ultra-high density block diagram for 200 watts to 350 watt power supply at the bottom of your screen, you will notice the diode bridge has been removed or gone bridgeless. This is because we are using a totem pole PFC, in this case the NCP1680, which jettisons the full wave rectifier for improved efficiency and smaller form factor. The NCP1680 is a CRM or a critical conduction mode MCU-less state machine based totem pole PFC controller that requires no firmware. So by design, the NCP1680 simply knows exactly what to do. The NCP1680, rated for up to 350 watts, drives two NVH-L065N65S3F 650 volt 65 milliohm MOSFETs configured in a half-bridge topology, switching at the line frequency of 50 Hz or 60 Hz for the slow leg, and as for the fast leg, the NCP1680 drives two NTH-L045N065 SC1 650 volt 32 milliohm silicon carbide MOSFETs configured in a half-bridge topology, switching from 120 kHz down to 30 kHz in frequency foldback depending on the load. The beauty of a bridgeless totem pole PFC topology is that any one given time, for the positive half cycle or the negative half cycle, there are only two devices in the conduction path. In contrast, a diode bridge PFC topology always has three devices in the conduction path. For our high-density power supply from 350 watts to 1 kilowatt, we return to a diode bridge using either the DFB20100 or the DFB2080. The NCP1618 PFC controller drives a single NVH-L072N65S3 650 volt 72 milliohm N-channel MOSFET power switch. The NCP1618 is an innovative multi-mode power factor controller. Depending on the current cycle duration, the NCP1618 autonomously navigates the optimal operation mode from continuous conduction mode, or CCM, to critical conduction mode, or CRM, or to discontinuous conduction mode, or DCM, with frequency fallback for an optimized efficiency over the line load range. In very light load, the circuit enters the soft skip mode. In addition, its high voltage capability eliminates the need for external startup and saves the permanent leakage they cause. Housed in an SOAC9 package, the NCP1618 incorporates all the features necessary for robust and compact PFC stages with very few external components. As for our ultra high density power supply solution from 350 watt to a kilowatt at the bottom of your screen, we revert back to a totem pole PFC bridgeless topology with the NCP1681 totem pole PFC controller. The NCP1681 is an MCU-less state machine-based totem pole PFC controller that requires no firmware. So by design, the NCP1681 simply knows exactly what to do. The NCP1681 is a multi-mode totem pole PFC controller, meaning it is capable of operating in fixed frequency CCM or current conduction mode, or constant on-time CRM mode or critical conduction mode, and valley synchronized frequency foldback for an optimized efficiency across the entire load range. With proprietary current sensing architectures and proven control algorithms, the NCP1681 allows for a cost-effective solution in a 20-lead SOIC package without jeopardizing performance. For our high-density power supply ranging from 1 kilowatt to greater than 3 kilowatt, we can use the DFB 25100 or DFB 2580 diode bridge. For PFC, we can use either the FAN 9672 2-channel or the FAN 9673 3-channel interleaved CCM or current conduction mode PFC controllers. Both devices fully comply with the IEC 1000-3-2 specification. Interleaved operation provides substantial reduction in the input and output ripple currents, and the conducted EMI filtering becomes simpler and more cost-effective. An innovative channel management function allows the slave channels to be loaded and unloaded smoothly in lower power level conditions according to setting voltage on the CM pin, improving the PFC converter's load transient response. Both devices incorporate a variety of protection functions, including peak current limiting, input voltage brownout protection, and tri-fault detection function. You will notice our LLC is located in the secondary side. I like to refer to the NCP4390 as a 2-for-1 because the NCP4390 is both an LLC controller and a synchronous rectifier controller built into a single device. The NCP4390 offers a wide operating frequency of 39 kHz to 690 kHz and is located in the secondary side. The NCP4390 drives two FDM S4D0912C 120 volt 4 milliohm N-channel MOSFETs in a half-bridge configuration in the secondary side. The NCP4390 also drives two NTH4L045N065 SC1 650 volt 33 milliohm silicon carbide MOSFETs, also in a half-bridge configuration in the primary side, with the help of an NCP51561 5 kV galvanic isolated dual gate driver, featuring 4.5 amp source current and 9 amp sync current capabilities. In this block diagram, the NCP51561 is not captured by an orange rectangle, and instead is captured by a small transformer symbol to signify the isolation between the primary side and the secondary side. As for our ultra high density power supply solution from 1 kilowatt to greater than 3 kilowatt at the bottom of your screen, we revert back to a totem pole PFC bridgeless topology with the NCP1681 totem pole PFC controller. The NCP1681 is an MCU-less, state machine-based totem pole PFC controller that requires no firmware. So by design, the NCP1681 simply knows exactly what to do. The NCP1681 is a multi-mode totem pole PFC controller, meaning it is capable of operating in a fixed frequency CCM or current conduction mode, or constant on-time CRM mode or critical conduction mode, and valley synchronized frequency foldback for optimized efficiency across the entire load range. With proprietary current sensing architectures and proven control algorithms, the NCP1681 allows for a cost-effective solution in a 20-lead SOIC package without jeopardizing performance. The NCP1681, rated for greater than 3 kilowatt, drives two NVHL065N65 S3F 650 volt 65 milliohm MOSFETs configured in a half-bridge topology, switching at the line frequency of 50 Hz or 60 Hz for the slow leg. And for the fast leg, the NCP1681 drives two NTH-L045N065 SC1 650 volt 32 milliohm silicon carbide MOSFETs configured in a half-bridge topology, switching from 130 kilohertz to 30 kilohertz in frequency foldback depending on the load. The beauty of the bridgeless totem pole PFC topology is that at any one time, for the positive half cycle or the negative half cycle, there are only two devices in the conduction path. In contrast, a diode bridge PFC topology always has three devices in the conduction path. After reviewing the past 11 block diagrams and returning to the easy-to-use switch mode power supply matrix, I think one can appreciate and value the very comprehensive technology solutions that onsemi offers to switch mode power supply design, scaling from 5 watts to 3 kilowatt and beyond, with many high density and ultra high density options to fit your power supply applications. So one thing I would like to highlight here in orange is the many instances where the wide bandgap silicon carbide solutions can improve efficiency as well as reduce physical form factor in this easy-to-use switch mode power supply matrix. I want to point out that all of the SiC devices here are basically the same 650 volt 32 milliohm SiC device, where the only difference is the package. Where you do not see an asterisk is a 3-lead device, and where you do see the asterisk is a 4-lead device. On this slide, we take a closer look at the 650 volt 32 milliohm silicon carbide MOSFET that we earlier highlighted in orange in the easy-to-use switch mode power supply matrix on the previous slide. On the right, you can see a side-by-side comparison between the 3-lead and the 4-lead package options, where the 4-lead package offers a Kelvin sense pin for the source terminal. This improves the total switching losses, which helps improve overall efficiency. For example, the 3-lead device datasheet specifies a total switching losses of 226 microjoules, while the 4-lead datasheet device specifies only 80 microjoules for the exact same operating conditions. In short, the 4-lead improves the total switching losses by a factor of just under 3x. Either way, onsemi has you covered for world-class switch mode power supply performance. Now let's take a quick look at our USB-C power delivery reference designs for 65 watt and 100 watts. On the left, you can see an image of our 65 watt Type-C PD reference design with a 26.5 watts per cubic inch power density, supporting PD 3.0, programmable virus supplies, and also BC 1.2. This uses an NCP 1345 quasi-resonant flyback along with an NCP 4306 secondary side rectifier controller and then an FUSB 15101 PD port controller. And this supports a full load of efficiency at full load of 93% and a standby power of 40 milliwatts. And then to the right, we've got the 100 watt reference design with a 24 watts per cubic inch power density supporting PD 3.0, including programmable power supplies, and DC 1.2. And of course, this is over 75 watts, so we need a PFC. And for that, we've got the NCP 1623, along with the NCP 1345 quasi-resonant flyback and the secondary side controller, the NCP 4306, plus the FUSB 15101 PD controller. And that has a full load efficiency of greater than 92.3% with a standby power of 50 milliwatts. And now I'd like to share with you a block diagram of our 3 kilowatt power supply with a little bit more detail than before, and this includes silicon carbide. Okay, so this is a more detailed view of our 3 kilowatt power supply for applications that include energy infrastructure, energy storage, and lithium-ion charging up to 15S or 15 cells in series. For applications like robotics, industrial drives and pumps, and power supplies. It includes PFC totem pole, LLC half bridge, and synchronous rectifier for our full bridge. And the peak efficiency is 94.2% at 115 volts and 96.5% at 230 volts. So looking down below from the left to right, you've got the AC input of 85 volts VAC to 264 volts VAC. On the far right, you've got your DC output, which is adjustable, either 48 volts, 62.5 amps, or 54 volts, 55.5 amps. Going back to the left, we've got our NCP 1681 total pole PFC controlling a slow leg and fast leg. For the slow leg, we've got silicon junction switches. For the fast leg, we use in silicon carbide. We're driving the silicon carbide with an isolated gate driver, in this case the NCP 5156X or the NCD 575XX family, 5 kV isolation. And for the silicon junction slow leg, we're just using the FAN 7191, a non-isolated gate drive. And so these two, slow leg and fast leg, perform the power factor correction. And then moving further to the right, you can see an LLC transformer with an integrated LR. And below that is the NCP 4390. That's our 2-for-1 combination secondary side controller and LLC controller. So you can see that feedback input goes to a resistor divider off the output on the far right. And that tells the NCP 4390 how to basically regulate the output. And it does that by driving both the secondary side and primary side. For the secondary side, in this case, we have a full bridge with 4 silicon junction MOSFETs driven by 2 NCP 81075 non-isolated gate drivers. And to the left, for driving the half bridge on the primary side using Elite SiC, we have the NCP 5156X or the NCD 575XX family of 5 kV isolated gate drivers. And so that, in a nutshell, is a summary of the 3 kilowatt power supply with a little bit more detail. And now let's take a look at our 7.2 kilowatt onboard charger block diagram, also using silicon carbide. Okay, so this 7.2 kilowatt onboard charger applications include EV charging for OBC or onboard charging level 1 or 2, or a power supply. The technologies include PFC 3-phase interleaved as well as an LLC full bridge, and the peak efficiency is 95.7% at 320 volts out and 95% at 400 volts out. And so on the far left, you've got your AC input 85 VAC to 264 VAC, and at the far right, you've got your DC output of 250 volts to 450 volts with a 16 amp max. Moving back to the left, you can see the fan 90, well, first of all, we have a diode bridge on the far left, and then following that, we have the fan 9673Q. That's our 3-phase interleaved PFC controller. It drives 3 different Elite SiC silicon MOSFETs, followed by 3 Elite SiC diodes. And we're using the NCV 51705 gate driver. It's a 6 amp source and sink that includes negative bias. And we're also, so further to the right, we've got the NCV 4390, that combination LLC and secondary side controller. So on the secondary side, it's controlling a full bridge, and on the far left, for the primary side, it's driving a full bridge, and we're making use of 2 5 kV isolated SiC gate drivers, the NCB5156X. And then we're also using on the far bottom right an NCB210R, which is a current sense amplifier. So the processor in gray knows what the current can do current sensing. And that's basically it. Thank you very much.
Thanks, Bob, for that great presentation. We already have several interesting questions, but I want to let our audience know that there's still time to submit your questions, again, using the Q&A tab. Okay, Bob, you ready to get started?
Sure. Sounds good. Thank you, Jeff.
First question, what improvements do you see with regard to EMC compliance?
Well, that's a pretty big subject, especially with the context of this presentation, where there's such a wide amount of power, going from tens of watts to like 3 kilowatt and a little bit above. But one of the things that most, if not all, of our controllers employ is a thing called spread spectrum. What that means is it'll have clocks, or I shouldn't say clocks. It'll have a high frequency signal that's driving these power switches,